Columbia, did his PhD in Berkeley, then postdocs at CERN and Fermilab, right? Yeah. And now he's a professor, full professor and chair of his department in Northwestern. And he's well known in neutrino physics, many things. I remember many of his papers I read, neutron scattering, dark side of the neutron oscillations, and then R5 evaluation. He also worked on supersymmetry. That's also I remember actually. I don't know. I was also part of this dual collaboration. And, he is now one of the leading experts in U.S. leading about neutrino physics. Okay. So we welcome him here, and he's going to talk today about the brave new world.
Okay. Yeah. So. All right, so thank you for having me, and thanks for coming at this unusual time. Let me know if the sound is weird, and we can try to tone it down a little bit, but I think it's working. So, so again, yeah, so thanks for the invitation. Thanks for coming. So this talk is about neutrino physics. And I always like to joke that if you're here because of literature, you'll be very, very disappointed. But here you don't have any humanities, so you won't get any literature students. So of course, this is just a joke on the title of a very famous book. One thing which I always like to tell people is that if you've ever read this book, it's not a very happy book. It's a very depressing, dystopian future book. And I hope to convince you that neutrino physics is not like that. It's a more upbeat part of the world. Also, the other thing I want to say is that this is meant to be a very simple talk. So if you happen to be an expert in particle physics or neutrino physics, my goal is for you to be disappointed. So I will not say anything that you don't know. And hopefully this is aimed mostly at the students and the postdocs and people who don't care about particle physics or don't think about particle physics on a daily basis. Okay, so just keep that in mind. So I want to start at the very beginning. So this is a picture of all of the fundamental particles as we know them. You may have seen different versions of this plot. So this is what the particles really look like, in case you're curious. And the most important thing is that you've heard about the particles. There are the quarks, there are the leptons, there are the force carriers, there's even the Higgs boson. There might be something called the dark matter that we don't know about. So the neutrinos are among some of these fundamental particles. And my job is to tell you about the neutrinos themselves and what we've learned about neutrinos and what are the types of questions we're trying to answer using neutrinos as tools. Of course, neutrinos are very special because they're very, 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 very abundant. So they are by far the most abundant matter particle in the universe, bar none. And they are also produced in lots of different places. So a very good place to talk about neutrinos is neutrinos are produced in the sun. So the sun, as everybody knows very well, is an intense producer of photons. It produces a lot of electromagnetic radiation, but it also produces a lot of neutrinos. And I'm not going to talk about solar neutrinos, but the important number to keep in mind, and that's something that you must have heard about if you've heard about neutrinos, is if you take a 1 centimeter square area, the number of neutrinos from the sun that traverses that is about 100 billions. So that means that about 1 trillion neutrinos are going through your body every second. Neutrinos are also produced by radioactive decays, especially by beta decay. So if you have something like a nuclear reactor emits a lot of neutrinos as well. And neutrinos are also produced when cosmic rays hit the atmosphere. Radioactivity is a thing that produces neutrinos. Here's another good number to have. So if you take a typical banana, it has a potassium in it. Actually, that's one of the things that bananas are good for you because it has potassium. That's something that you need. But if you have any amount of potassium, there's some radioactive potassium baked in. You can't get rid of it, by the way. So you're eating this radioactive stuff if you eat a banana. And it turns out that a typical banana produces about 1 million neutrinos every day. If we look further away in the universe, this is a picture of a supernova explosion. This is the before, and that's the after. This is the explosion of a supernova 1987A that happened in 1987. It didn't happen in our galaxy, but it happened in a nearby galaxy. And the thing that's you've heard about supernovae before is that supernovae, when they explode, they become brighter than their host galaxies. So it's a big deal, a supernova explosion. The thing that's less well known, and it's associated to this 1987A explosion, is that when a supernova of this type explodes, actually the vast majority of the energy comes out in neutrinos. So if you want, the light that's coming out of the supernova explosion is a very minute fraction of the physics that's going on there. Basically, the supernova is an event that emits a lot of neutrinos and a little bit of light. So the light is a thing that we can see spectacularly, but if we could see the neutrinos, it would be way more impressive. So again, it's a big, big, big neutrino factory. And of course, neutrinos are relics of the Big Bang. That's why I said they're the most abundant fundamental particles out there that are matter particles. So this here is a plot of the average density of the different types of particles in the universe. We are here. We're made out of protons, neutrons, and electrons. And there's a billion more photons per electron today. So basically, the universe is a big bath of photons and neutrinos. So if you look, the neutrino number is almost the same as the number of photons in the universe. So again, if you wanted to describe the universe very quickly, you would say it's a big mixture of neutrinos and photons. And then there's some matter as well. But the matter is a very, very tiny subset of the neutrinos and the photons that are out there in the universe. And again, the density is very high. It's about a few hundred per cubic centimeter. So every cubic centimeter in the universe has about a few hundred neutrinos in it, and a few hundred photons as well. And if you want to look for protons, the average density of the universe is about 1 proton per cubic meter. So the universe doesn't have a lot of protons in it, but it certainly has a lot of neutrinos. So neutrinos are absolutely everywhere. So if nothing else, they make up the vast majority of the universe together with the photons. So it stands to reason that understanding them is a good idea. Now, if you're completely new to this field, which I'm assuming you're not, you could be wondering, how come I don't know anything about this? I mean, there's this thing that's everywhere, and somehow I've never seen a neutrino before. And the reason is, of course, the neutrinos are ridiculously weakly interacting. So again, neutrinos are neutral. That's in the name. That means that they don't participate in electromagnetic interactions, and they also don't participate in the strong nuclear force. So there's another neutral particle that's very familiar to us, which is called the neutron. So the neutron is quite heavy, but it also participates in these nuclear forces, so neutrons are easy to detect, in many quotes. Neutrinos don't participate in that either. They only participate in what's called the weak interaction, and the weak interaction turns out is very weak, which is why it's called the weak interaction. And there's lots of famous numbers that people like to talk about. So for example, I told you that the flux of neutrinos from the sun, where the Earth is about 100 billion per cubic centimeter. So if for some reason you wanted to shield the sun, you wanted to shield the universe from the neutrinos that are being produced by the sun. So let's say I want to keep all of those neutrinos. I don't want them to be wasted and going out into outer space. In order to do that, you would have to build a dome out of lead that's about the width of the solar system. So if you build that, that will contain all of the neutrinos. But that's how hard it is to stop a neutrino. There's another number that's also nice to keep in mind, which is, I told you that for those neutrinos coming from the sun, about a trillion of them go to your body every second. And you can ask how many of those actually interact with you. And very roughly speaking, if you're lucky, you might get 1 neutrino interaction in your lifetime. Maybe a few people get 2 interactions or 0. So it depends on which mood you're in. So that means that neutrinos are, even though they're everywhere, they're very, very hard to detect, which makes them very, very hard to study. So of course, in order to study them, we need very big detectors that are very strange, and they have very large volumes, lots of material, and we've managed to do that over the years. So now let me turn to things that are more particle physics-like. So by the end of the last century, this is what we knew about neutrinos. It turns out that the 3 neutrino flavors, and the neutrino flavors are defined relative to how they interact via the weak interactions. So there's something called the W boson. The W boson interacts with an electron and the neutrino. And the neutrino that participates in this interaction is called the electron neutrino. There's another particle called the muon. It also interacts with the W boson and another neutrino, which is a different one. And that one we call the muon neutrino. And then there's a third one that's associated with a particle called the tau lepton. If you're not familiar with this, the muon is like the electron, but it's heavier. And the tau is like the muon, but it's heavier. And that's what we know about those particles. So there are these three different types of neutrinos, and what characterizes them is that these are three different states, and when an electron neutrino hits something, it knows how to produce electrons. When a muon neutrino hits something, it knows how to produce muons. When a tau neutrino hits something, it knows how to produce taus. So that's how we tell that these particles are different. So again, there are three of those. They only participate in what's called the weak interactions. Until the end of the last century, we thought that they had zero mass, and I'll come back to this in a second. And massless particles are weird, and I'm not going to spend too much time talking about that. But there are all kinds of weird things about neutrinos because they only participate in the weak interactions. And one of the main things about the weak interactions is that the weak interactions are chiral, for people who know what that means. And that means that, and they violate parity maximally. And what that means is the neutrinos have spin, just like the electron has spin. But it turns out we've only seen neutrinos with a particular spin projection. So we say that all of the neutrinos turn out to be left-handed in our universe, and all of the antineutrinos turn out to be right-handed. We've never seen an experiment violate that statement. And I'm not going to talk about the last thing. Now, it turns out that this picture that I showed you is actually wrong. Okay, and that's why life is very exciting. So by the turn of the century, we found out that we could produce electron neutrinos or muon neutrinos or tau neutrinos, and we could actually detect them in a different state. Okay, so that was the big thing that happened at the turn of the century. And the only thing that we needed in order to do that was to wait. So that means if you do an experiment where you produce the neutrino and you detect it right away, it doesn't change flavor. But if you allow the neutrino to travel a long distance, then it has a non-zero probability of changing flavor. Okay, so that's what we've discovered. And for people who've been around longer than me, for example, I want to remind you that the evidence for this is absolutely overwhelming. So when I was a student a long time ago, this was not true at all. There were these weird anomalies that nobody really understood and very few people cared about. But over the years, we've accumulated a gigantic amount of evidence from lots of different neutrino sources, lots of different types of experiments, and both muon neutrinos and electron neutrinos in the initial state. And we are very, very sure that the neutrinos know how to change flavor. By the way, there are Nobel Prizes associated to these discoveries. There's also this breakthrough prize, which is more money than the Nobel Prize. And the reason we're very excited about this is that not only it's kind of weird, but the only way of explaining that was to postulate that the neutrinos have mass. So I want to spend 5 minutes telling you what do these flavor changes have to do with neutrinos having mass. The idea is actually very simple if you know quantum mechanics. So it turns out that let's postulate that the neutrinos have mass. So that means that there's another way for me to define what a neutrino is. So I can call them, neutrino 1, 2, and 3, and they have masses m1, m2, and m3. And these are the names that we came up with. They're not our best work in terms of coming up with names. They're very boring. But nonetheless, there are these ways of defining neutrinos by their mass. And of course, I just told you that we can also define the neutrinos by their interaction. So the question that you want to ask is, so, what does the electron neutrino have to do with these neutrinos that have a well-defined mass? And because of quantum mechanics, the electron neutrino doesn't have to be any of these, but the electron neutrino can be a linear combination of these. So the statement is that the electron neutrino is actually a linear combination of neutrinos with well-defined mass. And the muon neutrino is some orthogonal linear combination of these neutrinos with a well-defined mass. And the tau neutrino is another orthogonal linear combination of these neutrinos with a well-defined mass. Now, why is that important? That's important because you have to ask, what does it mean to be a neutrino with a well-defined mass, really? So, it's not like we put a neutrino on a scale and it measures a mass. When we're talking about mass, we mean the inertial mass. And the inertial mass for us means that if you produce a neutrino and it's propagating in empty space, the mass states are the eigenstates of the propagation Hamiltonian. Okay, so a neutrino with a well-defined mass is an eigenstate of the Hamiltonian that describes how neutrino states propagate in vacuum. That's not a very sophisticated statement. It just means that if you produce one of these mass eigenstates, the way its wave function will behave in space-time will look like a plane wave. Okay, so there's some e to the minus I et, and then there's some e to the plus IPX. So nothing spectacular here, just a regular plane wave. And of course, it's a plane wave where the energy and the momentum satisfy the regular dispersion relation that you're probably familiar with. So that's what a mass eigenstate is. This is exciting because the electron neutrino is not an eigenstate of the Hamiltonian. It's a linear combination of eigenstates of the Hamiltonian. And if I postulate, just to make my life better, that there are only two of these neutrinos, then the electron neutrino is a linear superposition of nu1 and nu2. And the mu1 neutrino is a different linear superposition of nu1 and nu2. That means if I produce in some point in space-time an electron neutrino, and this system evolves, it does not evolve as an eigenstate of the Hamiltonian. So because it's not an eigenstate of the Hamiltonian, each component of the electron neutrino does evolve as a plane wave, but it's a plane wave with a different phase. So this means if you measure your neutrino a bit later on, it will no longer be the electron neutrino, but it will have some non-zero probability of being a mu1 neutrino. So if we wanted to calculate what's the probability that I produce a neutrino somewhere, and I measure it far away sometime later at a different point, what's the probability that you are born as an electron neutrino and you're measured as a mu1 neutrino? It looks something like this. In order to make your life simpler, you can make some approximations. And the approximations have to do with the fact that the neutrino masses are very small and the neutrino energies are very large. So the energy and the momentum are almost exactly the same. So you make some approximation like that. And you end up with a formula that describes this probability that the electron neutrino is measured as a mu1 neutrino. And you get some very, very familiar expression. So again, if you've all taken quantum mechanics before, and I mean the undergraduate level quantum mechanics, you probably solved the two-level system. It's a very nice system to solve. It's very easy. I could do it on the blackboard right now and not make too many mistakes. And the key point is that this is exactly what the neutrino oscillation is. It's a two-level system in this flavor space. And these can oscillate, and they undergo what looks like Rabi oscillations. And of course, instead of oscillating like delta E times T, the relativistic equivalent of that looks like delta m squared L divided by the energy of the neutrino. So it's just something that looks like this. So it oscillates. It's characterized by an amplitude that has something to do with this mixing parameter, which tells you what these linear combinations here are. And then there's a frequency associated to that, or some oscillation length, which has to do with the differences of the neutrino masses squared. So that's the idea. So now we have all these data, and we want to see if the data are explained by this hypothesis. In the real world, we have three neutrinos, so we do the three neutrino version of this. When we do the three neutrino version of this, we have more mixing parameters. We have a CP odd phase, which I'll talk about in just a second, and we have to decide what the masses look like. So if we take this hypothesis, which again is very simple, if you work on it, you can learn it very easily. It's not rocket science. And you can ask, does this hypothesis explain all of the data that we've collected over the last 30 years? And the answer is yes. And not only that, we've done enough experiments that we can measure these parameters that describe the neutrino masses and describe the neutrino mixing. And by now, we've actually measured these parameters quite well, with some exceptions that I'll talk about in a second. And I want to pause here because for people who even are familiar with neutrino physics, they are often not impressed by this. But I want to remind people that when I was in graduate school, let's say 30 years ago, not only had we not measured any of these parameters, we didn't even know we had to. We didn't know they were parameters that were there to be measured. There was not physics that we knew about. So we've gone from not knowing that this is something we had to worry about to actually measuring these mixing parameters at the percent level in about 30 years. Now you might be wondering, 30 years sounds like a really long time. But in particle physics, it's not a really long time. Particle physics is a very slow subject where our experiments take a long time to do and to build and to run and to analyze the data. And there's a lot of examples of that. Maybe the most dramatic one is the Higgs boson that you've probably all heard about. The Higgs boson was postulated in the 60s, and it was ultimately detected in 2012. So that's about 50 years. And it's not like we weren't trying. We were trying for a really long time. But that's a 50-year gap. And especially for neutrino physics, it's been tremendous progress. We've been learning a lot about neutrinos very quickly. There's still some things we don't know, and I'll come back and tell you about those in a second.
So according to this
Yeah,
data, one of the neutrinos can still be massless?
that is completely correct. Yeah.
And what do you mean by short baseline anomalies?
Yes, I'll mention that. So what happens is this is true for all of the neutrino data, but there are a couple of data that we don't understand. So there are a couple of data that look weird, and they're not explained by this formalism. And the problem is these are experiments where we don't give the neutrinos enough time to oscillate, so you wouldn't expect to see anything. But somehow we see something that kind of looks like an oscillation, and we're still making sense out of that. Whatever it is, it doesn't fall into this formalism. Yes?
Why do you have 490 units for the data set?
So this is a big range. Oh, this is probably, it must be 305.
Oh, yes.
This is a typo.
Yeah, I know.
I could have said that it wraps around, but I think it's just a typo. So yeah, don't pay attention to the numbers. Those numbers are actually correct. I had not noticed that one before. But yes, there's no 405 degrees. Although there could be, because you can always wrap around. So if you're a theorist, which many of you are, we're very excited about neutrinos. And the reason we're very excited about neutrinos is that we found out that their masses are not zero. And on top of that, we've also found out that they're very, very, very small, even though they're not zero. So here's a cartoon of the masses of the fermions in the Standard Model. And there's a lot of things that jump out at you if you stare at this picture. One is, of course, that all of the charged fermion masses are up there in the heavy part of the plot. And the neutrino masses live all the way down here. They are definitely below an electron volt. We don't learn that from oscillations, but we learn that from not seeing neutrino masses in other types of experiments. We also noticed that, and so that's just, again, this is a log scale. So already an impressive statement about particle physics is if you want to fit all the masses into one plot, you need a log scale, and you need something like 15 orders of magnitude. So I always like to tell people that somehow we can live day to day and have one fundamental particle that weighs more than 100 GeV, and then have another fundamental particle that's 100 times lighter than that. And they're all fundamental particles. And we don't worry about that. A lot of people worry about that. But I think the message is that the charged fermion masses span about 5 orders of magnitude, and they're kind of organized in some nice looking way. And the neutrino masses are very, very light. And on top of that, in this bluish region here, there are no particles that we know about. So the statement we like to make is the neutrino masses are very different. So different is not a physics word, but they're very different. So that's what you want to get out of this. Now, that's one thing that's weird, is that the neutrino masses are small. It doesn't mean anything. So this is just to indicate these are the charged leptons. These are the down type quarks. These are the up type quarks. So I should have done up type this way, down type that way. It's too late now. And the other thing that we're very excited about as particle physicists is that neutrino masses are evidence that the Standard Model is missing something. So neutrino masses is evidence for new physics. So let me tell you a little bit about that. So again, this is aimed at the students. So there's this very nice picture that you've seen before, but it's actually not just a picture. It's a mnemonic device to remind us of the Standard Model of particle physics, which is a relativistic quantum field theory. And relativistic quantum field theories are kind of amazing. They're very hard, and they are the thing that we were driven to after a lot of time doing research in particle physics. And it's the result of trying to combine special relativity with quantum mechanics. If you want to have those two concepts play together nicely, you are driven towards a quantum field theory. What's also underappreciated in the way that we use particle physics is that quantum field theories are incredibly constrained. Most quantum field theories that you write down are not consistent. They don't make any sense. They predict something that's not physical. And we know exactly what it takes to write down a consistent quantum field theory. So it turns out that if you look at the particles that we know about and the rules that we know about, and you write down the Lagrangian, neutrino masses are predicted to be exactly zero. There's no wiggle room. There's nothing you can say, oh, maybe there's a lot, so it's not allowed unless you do something. So that's what I wrote down here, is that somehow we need some new stuff out there to make up non-zero neutrino masses. And the point is, even though we know that we need some new stuff, we have no idea what that stuff is because we haven't seen it yet. So we know that there's something missing, but on the other hand, we have no idea what that something is, and it could be lots of different things. So here's another way of saying the same thing, is that again, we know that there have to be new fields out there, but we don't know if these new fields are bosons or fermions. We don't know if they're charged. We don't know if they're light. We don't know if they're very heavy. We don't know if they're easy to see in an experiment or if they're impossible to see in an experiment. So that's kind of where we are. There's a few other things, by the way, in particle physics land that we also don't know. And they're kind of the big questions in particle physics. One has to do with the Higgs boson. We've made a lot of progress there. And we're all kind of disappointed that the minimal thing that we came up with 50 years ago works really well. But that's life. Somebody got lucky 60 years ago. There's this thing called the dark matter. We don't know what it is, but it probably is some particle that's not amongst the particles that we know about. We worry a lot about why the universe has a lot of matter in it. Remember, I told you that there's this 1 billion gap between photons and ordinary matter in the universe? That's actually too big. If you make a prediction about how many protons there should be, that number should be more like, I think, 10 to the 18, minus 18. So we're off by about 8 orders of magnitude, which is good for us because otherwise there would be no stuff in the universe. But we don't understand why that happened, and it seems to be a particle physics question. And then there's this whole thing about dark energy that I don't know anything about. But some people claim it has something to do with particle physics. And we don't know. So let me just say a few words about why neutrino masses are different. And I think if you don't know anything about particle physics, this may be not accessible, but that's fine. So we've all heard about masses. If you've heard a little bit about particle physics, we spent a lot of time talking about the origin of mass. And what happens is all of the masses of all of the particles that we know about, the fundamental particles, I'm not talking about the proton, but all of the masses of the fundamental particles, they come from what's called the Higgs mechanism. So they have something to do with the Higgs boson. And that's ingrained in the structure of our model of particle physics. So the neutrinos are not an exception. The neutrinos they're friends of the charged leptons like the electron and the muon, so they also need to get a mass from the Higgs boson. So in that sense, the neutrinos are the same. What makes the neutrinos interesting is that they have choices. So they need to get a mass from the Higgs mechanism, but they don't need to get a mass just like everybody else. So there are 3 broad kinds of choices you can make. One is that the neutrinos do get a mass like everybody else. And if you want to do that for the neutrinos, you actually need to add a new field, because a mass term in particle physics is a marriage between 2 different fields, and the neutrino is missing a spouse, let's say. So you need to invent another particle that can combine with the neutrino to give it a mass. In that scenario, you can have the neutrino masses be very similar to everybody else's mass. And if this turns out to be the case, there's some interesting consequences that I can talk about if people ask. But that's one possibility. Another possibility is that maybe there's another Higgs boson out there, and that Higgs boson is designed to just give the neutrinos a mass, but it doesn't give anybody else a mass, and vice versa. People like this idea in the abstract because it helps explain why the neutrino masses look so different. It could be that all of these particles get a mass from one Higgs boson, and maybe the neutrinos get a mass from a separate Higgs boson, and that explains why everything looks so different. Then there's a third choice, and the third choice is the more complicated one, and it's also the one that everybody likes, because we like very complicated things. And the idea is that maybe the neutrino masses are a combination of the Higgs mechanism and some other source of mass. And when those 2 things act together, the neutrino masses come out. People like this idea because it also allows you to explain why the neutrino masses look so different. And people also like this idea because it's the most consequential idea. It's basically telling you that, again, in the standard model, there's one source of mass, which is the Higgs field. But it's telling us that there's another source of mass, which in principle has nothing to do with the Higgs field. And the neutrino is our first evidence of this new source of mass. So people get very excited about that. You can speculate, maybe the neutrinos and the dark matter are secretly related in some way, and that explains everything. We try to do stuff like that. We have no evidence that this is true, but we have no evidence that it's false, so we keep working. So that's the kind of, these are the qualitatively different things you can do in order to give the neutrinos a non-zero mass, and our job is to find out which is the correct one. And in order to do that, we need experiment. So you can theorize as much as you want, and you can have your opinions, but that matters nothing. You have to actually do an experiment to check if one idea is different or better than the other one. So this is just a cartoon of all of the possible new mass scales there might be out there, and they would explain the non-zero neutrino mass. And these are all different types of phenomena where you might see evidence for that scale, for this new mass scale in nature. And again, there's all different kinds of completely different types of experiments or completely different types of phenomena. And depending on what this new mass scale is, you would see this physics in different places. So that's kind of that's the challenge for us, is that we can look for the origin of neutrino masses in 200 different ways, and they're all good ways to look for it. So in that sense, it's a little bit like dark matter as well. So we can postulate that the dark matter is some new field, and we can ask what are the properties of this field that make it qualify as a dark matter. It's things like how much it interacts, what its masses are, and then you have to look for it. And then the way you look for it depends on the properties of the dark matter. So if the dark matter is ridiculously light, you look for it in one way. If the dark matter is heavy, you look for it in a different way. If it's ridiculously heavy, you look for it in a totally different way. And if you ask what's the best way of doing it, we have no idea, because we don't have any evidence that any one of those is correct. So we kind of have to look everywhere. And the origin of neutrino masses is in the same category of things to worry about. So again, this is a list of the things that you need to do in order to try to find where the neutrino masses are coming from. And I'm highlighting here neutrino oscillations, because that's one thing we're making a big investment in, and it seems to be a good idea. And that's kind of what I wrote down here. So this is important to keep in mind. So I told you that we've learned a lot about neutrino masses from neutrino oscillations. We've actually measured a bunch of stuff really, really precisely. And the question always comes up, why should we keep doing these neutrino oscillation experiments? They're expensive, they're weird, they take a long time, and should we be doing something else? And one thing I like to remind people is we've only seen neutrino masses in neutrino oscillation experiments, ever. In the entire history of physics, we've been looking for the effect of non-zero neutrino masses for a long time. So again, neutrinos were invented in 1930, and then people wrote down a theory for their interactions in, I think, 1933. That was Fermi. And Fermi also wrote down a way to look for the neutrino mass by studying beta decay. So this is in the mid-1930s. It's 90 years ago. And we've been trying to do that for 90 years. And we have not succeeded yet. So the neutrino masses are very, very small. Nonetheless, we can see them in oscillations. So that means if you want to learn about neutrino masses, it feels like it's a no-brainer to do more of these experiments. It doesn't mean you're going to get an answer, but it feels like it's a good idea. So that's one way of thinking about that. And we have a lot of ongoing oscillation experiments. We have a lot of really exciting experiments coming online very soon. So there's a lot of work to do in order to understand what these oscillation experiments can do. Again, there are big experiments in Japan and the United States. There's an amazing experiment that hopefully will start running next year in China. And all of these experiments will teach us a lot of interesting stuff about neutrinos. And then there are also things like IceCube and atmospheric experiments and stuff like that. So let me tell you a little bit about what is the stuff that we don't know about neutrinos. One thing which I didn't tell you about is that we know the differences of the masses squared. So these are supposed to represent the masses squareds of the neutrinos. And we've measured these differences at the percent level, 2%, 3%, 4%. But we've never done an experiment where we can see the two oscillations at the same time. And the consequence of that is that we don't know how the masses are ordered. So the masses could be ordered in this way, 1, 2, 3, but they could also be ordered in this other way. So this is called the normal ordering, and this is called the inverted ordering. These are just names. Clearly, normal doesn't mean anything. But the masses could be ordered in two different ways. The other thing that's represented here, by the way, are these colors. And these colors are supposed to represent the elements of the mixing matrix. But it's not important for this discussion, although it's important for one thing. So let me say it. So for example, if you look at neutrino number 3, it has about a 50% chance of being a tau neutrino. That means if you could take one of these neutrinos and you made a flavor measurement, the probability that you would get tau flavor would be the fraction of this bar that's colored blue. And the probability that you would get a muon flavor would be the fraction of this bar that's colored green. And the probability that you get electron flavor is the fraction of this bar that's colored red. So you notice that neutrino number 1 has a lot of electron in it. Neutrino number 3 has not a lot of electron in it. And then all the other states have a fair amount of muons and taus in it. So what are the things we don't know? One thing we don't know is that there's something called CP violation that allows the neutrinos and the antineutrinos to oscillate differently. And that's governed by a parameter in my mixing matrix that's a complex phase. We don't know what that is. So that's one thing we don't know. There's a funny question that people like to ask, which is if you look at neutrino number 3, you notice that it's a 50% green and 50% blue. You can ask, why is that? The answer is because I drew it that way. But the question really is it? I mean, is it exactly 50-50? Is it more green than blue, or is it more blue than green? And we don't know the answer to that. Our measurement is not precise enough to determine that. Now you could ask, who cares? I mean, it's more than 50 or less than 50 by a little bit, but some people care a lot. So if you try to understand whether this chaotic structure has some structure in it, there's some meaning that's missing from here, that might be contained in this kind of information. Of course, we don't know which picture is correct. And I do want to say these are two very different pictures, right? So the picture on the left allows the masses to be all very different. That's why it's called normal. So it could be that this mass is a lot smaller than that one, which is a lot smaller than that one. But if it looks like the picture on the right, these two masses have to be almost exactly degenerate at the few percent level. That would be very weird, to have two particles that have almost exactly the same mass. It feels like it means something. So people get very excited about that too. So they're all, yeah.
So we care about the precision of theta 2 3 because we want to check unitarity of the.
Oh, and then there are all kinds of, yeah, good. So there are all these things we haven't measured. This theta 2 3 we care about because of flavor models. But the one thing that you mentioned, which is more important, is the reason we want to measure these things and the reason why we want to measure the other mixing parameters better is not just because we like to measure things well. It's also because we want to check if this model is actually correct. So not only do we want to measure everything, we want to really measure everything very well. And again, the reason we do this is not because we like to measure things very well, but it's because it's a great way to test if our formalism is correct. Right? We can, asking, am I missing something, is something that you can answer by doing precision measurements. And that's kind of what I wrote down over here. So the goal here is not to go down some laundry list of things that I haven't measured yet, but it's actually to test if I've measured things precisely enough. So I want to give you an example from quark flavor physics. So if you're not doing quark flavor physics, you may never have seen a plot that looks like this. This is an old plot. And basically, these are measurements in the quark sector. You measure kaons and B mesons and D mesons and so on. And here are two parameters, rho and eta. And they're kind of like mixing parameters, theta 1, 3, theta 2, 3. And you notice that there's a bunch of colors here. Every color here is a measurement. And it's a measurement of the same thing. And you notice that we've tried to measure those two parameters in like 20 different ways. And you can say that's sort of a waste of resources, right? There are only two parameters. If I did two measurements, I could be done and measure those parameters very well, and I could go home. So why did we do this? Okay, the reason we did this is because we wanted to measure these parameters in lots of different ways. And we wanted to check if they all agree. because if they don't agree, it means that we're missing something. And sadly, they all agree. They all meet at this point here. And the question is, how do we do the same thing in the neutrino sector? I will say this is a 2009 plot. There is a 2019 version of this plot, which looks exactly the same, except that the bands are narrower, but they still meet at a point. So somehow, that model is working very well. So we need to learn how to do this in the lepton sector, and that turns out to be very hard. And so first of all, the amount of information we have today is not a lot. So again, this will be more technical, but here's my mixing matrix. And you can ask, so I told you I can measure all these mixing parameters at the few percent level. But it turns out that when we do that, we're kind of cheating. And in one way we're cheating is that we're assuming, for example, that this matrix is unitary. If we didn't assume that, you can ask, what do I really measure? This is a list of the stuff that I really measure. And you notice that we don't really measure too many things. We can measure these things in red. We can measure this thing in blue. Actually, we can do this one really well. And we can measure these things in green. But we have no direct access to these numbers here, to zeroth order. Okay, so we don't really measure these things very well. And we only get these precision measurements because we're doing things assuming that the matrix is unitary. If you violate unitarity, life is much harder. So we still have a long way to go. And that's where neutrino experiments being hard becomes a problem. Because we don't have, it's not like in the quark sector where we can measure 100 million things. Here we don't measure too many things, so we have to be smarter. So here's an example of where we are today in terms of measuring. This is the equivalent of this plot for neutrinos. If we take all of our data, the allowed region is this purple region here. So you should look at this allowed region as the equivalent of this little blob over here, but in the neutrino sector. So we haven't really done a very good job. By the way, this one is just another version of the unitarity triangle. But with the new experiments like Dune and Hyper-K, we hope to reduce that to this small region that you see here in red, for example. Okay, there's more structure here, but I'm not going to talk about that just now. I want to show you something different. Remember I told you that our job is to measure things in different ways. So here's one thing we could do. So for example, we can measure theta 2,3 and we can measure theta 1,3 in lots of different ways, okay, by doing different experiments. This is one type of oscillation experiment. This is new tau appearance. It's a different oscillation experiment. This is a reactor experiment. And this is disappearance and appearance. And all of these experiments can measure these two parameters, and they translate into a curve in this plot. And you notice that they all agree, and they all agree and they live over here, and that's the allowed region for these two parameters. If we go to the future with Dune and Hyper-K, there's going to be, the regions will get a lot smaller, and they're all going to agree at this really tiny point that looks like the size of my pointer over here. So that's how much better things will do, and you see how much better we'll be able to test whether there's something that's gone wrong in our experiments. So here's an example of that. If I assume that the matrix is not unitary, we could be in a world where you look at all the measurements that you can do for these two parameters, and you notice that there's no place where they all overlap. So it is possible by 15 years from now that we might be in a world where our measurements don't close, that there's something there that's missing, and that would be very exciting, and it could be revealed by oscillation experiments. Okay, so yes. And there's a fun thing about this plot is that it shows you how important it is to the tau appearance, because the green curve is the thing that's telling you that you're not closing the story. This is by design, of course. This is a phenomenology paper. But their job was to exemplify what could happen, and also to show how looking for tau appearance in Dune can be very important. So yeah, this is a very nice plot. Of course, this is all simulation. Life will be whatever life turns out to be. So I want to say something about CP violation. And CP violation is a very important thing in particle physics. It has lots of different applications. And it has to do with the fact that the weak interactions allow matter and antimatter to be treated differently. So it is possible that you can do a process that only involves matter and a different process that only involves antimatter, and the answers are not the same. And that's CP violation. So it's an interesting question. And in the standard model of particle physics today, without neutrino masses, there are only two parameters that govern all possible CP violation. So one of those is a phase, a complex phase that lives in the quark mixing matrix. And it turns out that 100% of all CP violating phenomena ever observed, ever, come from this one parameter in the quark mixing matrix. Okay, and we can explain everything. That's related to that picture that I showed you before. Secretly, there's another parameter that lives in the QCD sector called theta QCD. We don't like to talk about it because we don't know what's going on there. But it's another parameter that's also parameterized as a phase. And as far as we can tell, that number is consistent with 0. And it's actually known to be less than about 10 to the minus 11. Okay, so there are two mixing parameters. They're both phases. The quark phase, by the way, is about 70 degrees. And the theta parameter is 10 to minus, less than 10 to the minus 11. If you allow neutrino masses to be non-zero, there's at least one more CP violating parameter. And of course, the question is, what do you think that parameter will be? And the answer is we have no idea. Most people will say it's some random phase, it's some number. But it could be 10 to the minus 11, for all we know. So we have to measure it. And of course, we're going to be increasing our understanding of CP violation by 50%, from 2 parameters to 3. So that seems exciting. And I think I'm going to skip this. But that's how CP violation works. This is how it looks. So if you did an experiment measuring your mu to nu e with neutrinos and your mu to nu e with antineutrinos, literally the probabilities are different. So this is as a function of some random, like the distance over the energy. And let's say antineutrinos could do the blue curve, neutrinos would do the black curve. So it looks like a good, easy measurement to make, right? You sit here, you see if you get this number different from that one. So that's literally how CP violation works. It's very, very simple. It's kind of a textbook physics. It's way easier than how it works in the kaon sector. For people who've studied particle physics, it's kind of annoying to explain all the decay parameters and the CP violation in the mass and in the decay and blah, blah, blah. Here it's very simple. It's a totally trivial process. This is where we are today with CP violation. CP violation is parameterized by this parameter delta. And life is confusing. So we have 2 experiments. One experiment likes to live in this blue region. This depends on how the masses are ordered. Let's only look at the top one. And the other experiment likes to live inside of this dark contour. And it's ironic they perfectly not overlap. So we don't know what's going on. We need better experiments. And that's what we're doing. So we're working on better experiments. So for the next couple of minutes, I want to mention that, of course, I'm telling you that we have to do oscillation experiments better in order to decide, in order to look for some new phenomenon. So one question you can ask is, what could this new phenomenon be? One thing is to work in the abstract and say, we want to do better. The other one is to say, is there anything that you could see with these types of experiments? Yeah?
So the previous plot tells that inverted ordering is more preferred.
That's a good question. And you have to read it very carefully. So what happens is when people are doing these fits, they actually allow for the 2 mass orderings and they fit them together. And actually both experiments prefer the normal ordering. So the reason this inverted ordering contours look smaller is because they're less favored. So none of the experiments can tell one ordering from the other, but ironically they both prefer the normal ordering. When you combine them together, mysteriously, they actually like the inverted ordering better for the reason that you're asking, because they seem to agree more. But that's just an artifact of lots of things. So it's statistics. What this means is that you need better, more data. That's every time things look confusing, that's always the answer. You need better data. So that's kind of where we are. But that's an interesting analysis that the experiments have done themselves to figure out what happens when you combine the data. And they have a slight preference for the inverted ordering, but not because any one experiment likes the inverted ordering, but because they disagree less if the ordering is inverted. That's not the situation you want to be in. It happens, but it's not the situation you want to be in. Okay, so coming back to this, you can ask, what could happen in terms of neutrino physics? One possibility is that you see new neutrino states. So if there are new neutrino states, then your mixing matrix is bigger, and that means that the 3 by 3 submatrix is not unitary. It could be that there are new forces that the neutrinos feel with matter. So maybe the neutrinos see the weak interactions, but there's some new interaction we don't know about that's a little bit weaker than the weak interactions. And they would show up in neutrino physics, and they actually modify how the neutrinos propagate through a material. So that's called the non-standard interactions, and that's something we can look for. There's a whole bunch of other interesting questions you can ask about neutrinos if they have mass. So one question you can ask is, if the neutrinos have mass, can they decay? Again, massless particles are not allowed to decay, but massive particles can decay. A different question you can ask that has to do with mass, even though you may not have thought about it before, is if the neutrinos have mass, they could have a magnetic moment. Just like the neutron has a magnetic moment, the neutrino is allowed to have a magnetic moment. And by the way, in the standard model, without any new physics, just non-zero neutrino masses, the neutrinos do decay. And they do have a magnetic moment. That's not optional. They must decay, and they must have a magnetic moment. And again, because the neutrinos are heavier, the heavy neutrinos are allowed to decay via the weak interactions into the lighter ones. And they can also have a magnetic moment. The problem is in the standard model, you can calculate these things, and the neutrino lifetime is like 10 to the 40 years, 40. It's a very long lifetime. We don't need to worry about it. And the neutrino magnetic moment is something ridiculous, like 10 to the minus 20 Bohr magneton. If it doesn't mean anything to you, it's very small, trust me. It's a very, very small magnetic moment. But if there is new physics, those things could be very different, including both the lifetime and the magnetic moment. So those things can show up in neutrino oscillations. And of course, you can have some weird stuff also. And I will mention those just at the very end. So and those are things that you can probe with neutrino oscillations. And it turns out you can probe very well. So I'm going to skip these case studies because of time. This is just to show, here's the Dune experiment. This is what the data should look like in some channel. If you have a new neutrino state, it would look like that. So that looks like something you can see. And then I'm going to skip the other stuff. This is, again, people can ask me later. OK. So I have a couple of minutes. So one thing is that you can see new physics in the neutrino oscillations. Another thing that's become very popular now is these neutrino experiments are complicated. And one thing and the way they work approximately is that you take protons, you shoot them on a target. And the goal here is to take as many protons as you can. So that's what we're working on in terms of accelerator physics. You shoot they don't have to have a lot of energy, but the key thing is lots of protons. You produce a lot of mesons when you do that, pions, kaons, if you're unlucky, heavy stuff. And then the pions will decay, and they decay into neutrinos. That's how you get your neutrinos. So you take the pions, you make them all go in the same direction. They kind of decay in a forward direction. Then you get a neutrino beam. By the way, calling the neutrino beam a beam is a very generous thing. The neutrino beam is gigantic. And by the time the neutrino beam gets 1,000 kilometers away, the size of the beam is about 1 kilometer big. So if you ever worry about how well can we aim the neutrinos, we don't have to aim very well, because the beam is huge. So you get a neutrino beam this way, and people get very excited because we also measure the neutrinos nearby in order to characterize what the neutrino flux looks like. So we build a detector nearby. So if you have funny new particles that are being produced together with the neutrinos nearby, you can look for them in this faraway place. You can look for dark matter particles. You can look for new heavy neutrinos. You can look for axions. So there's a lot of new physics you can do just because you built a new oscillation experiment. So I'm going to skip that. Somebody asked about the short baseline anomalies. We have 2 experiments that are infamous, the LSND experiment and the mini-Boone experiment. So this is what their data looks like. Expectations are green plus red. And you see that the data are much taller than that. And you can explain that with neutrino oscillations. The problem is it's not one of the oscillation frequencies that we know about. It's a new one, which of course doesn't fit into the picture that I told you about. And then this is the mini-Boone data. Again, you expect everything that's colored here, and you see an axis of events. It doesn't look very impressive, but it's kind of impressive. It's like 3.8 sigma or something. Oh, 4.8, here it is. 3.8 was this one. It depends on who you ask, the 4.8. And we have this other anomalies in the short baseline reactor experiments that also see fewer neutrinos than what we expect. And then there's a whole slew of different ideas to try to explain what's going on there. And we've been thinking about this for a long time, so the number of ideas is very large. And of course, there are many, 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 many more ideas which are ruled out. So that's good. So we have a fewer ideas that survive. And we're building new neutrino experiments, and they're running right now at Fermilab. There's something called the short baseline neutrino program at Fermilab. And they are designed to try to find out what's going on with these short baseline anomalies. So it's very exciting. And now let me conclude. And I think I'm exactly on time, but people can ask questions later. So again, I showed you this picture in the very beginning. And for people who know a little bit about particle physics, there's something wrong with this picture. And the reason is the neutrinos are wrong. And the reason is, finally, that all of the particles here, including the photon and the gluons and the Z boson and the W boson, the electron, muon, and tau, and all of the quarks, these are all particles with a well-defined mass. That's how we took pictures of them. They're all the particles with a well-defined mass. The neutrinos are not. These are not the eigenstates that have a well-defined mass. These are interaction states. They're not real particles. These are the real particles. They look like that. They're linear combinations of E, mu, and tau. So that's what we learned in the last 20 years, is that somehow the right picture should look like that. So we need to go back and redraw these. By the way, I do have a plush version of these guys, it turns out. It's really nice. It's in my office. I forgot to bring them, but they exist. So there they are. So that's the real big picture, is that somehow the way that we talk about neutrinos has changed. So here's sort of a quick summary. So we know very little about that new physics. So we know that there's some new physics, but we know very little about that. We have some hints. The biggest hint is that neutrino masses are very small. I didn't talk about this at all, but we also like to say that neutrino mixing is very weird. And you can say weird compared to what? And it's very weird compared to quark mixing. So quark mixing is very orderly. Neutrino mixing is very chaotic. We don't know if that means anything, but it sounds important. We need more experiments. I mean, this is a very data-driven field in the sense that we need more information in order to make progress. And of course, I talked a lot about neutrino, precision measurements of neutrino oscillations, and I try to convince you why that's interesting and important. The final bullet that I have here is there's a lot of room for finding interesting stuff when you do neutrino oscillations. I think there are different ways of thinking about that. My favorite way of thinking about that is that, remember I've said this many times, neutrino masses are very small. And we've been looking for them for 90 years. And we can only see them in neutrino oscillation experiments. You can ask, why is that? And what's so special about neutrino oscillations? And the answer is quantum mechanics. And it's actually quantum mechanics interference. So neutrino oscillations are like an interference device. And if you've gone to enough physics talks, you know that interference devices are ridiculously good at measuring very difficult things or measuring things very precisely. So the neutrino oscillation is our interferometer, and we can see these very tiny effects, including the neutrino masses. So if there's other very tiny effects out there, they might be very difficult to see anywhere, but they might show up in neutrino oscillations. So that's something that's very important to keep in mind. So the last thing I have has to do with the Brave New World for people who've actually read the book. I told you that that's a very dystopian book. Actually, nowadays, if you read it, it's not as dystopian because we've had too much experience with the real world. But it's still very dystopian. I won't tell you the end, but it's very sad. But nonetheless, if you actually read the book, this phrase, "a brave new world," is a quote, and it's actually a quote from Shakespeare. And that's exactly where the title of the book comes from. And it's this quote from Miranda from The Tempest. That's the weirdest of Shakespeare plays. And it's actually a very happy quote. And if you remember, there's a tempest, there's a boat, and the boat sinks, and then some survivors come to the island. And it turns out that this woman had never seen other people before. So she was very amazed by these people that were coming in, and she had no idea what they were, and she was very excited. So again, neutrino physics is very exciting, so I'm hoping to leave you with this image as opposed to the pill that we were talking about in the beginning. So I'll stop here. Thank you.
Thanks for the wonderful talk, Andrew. Any questions?
So maybe you misunderstood, but I think in the beginning you said that there's no way you could incorporate non-zero neutrino mass in the standard model. But towards the end you said that using standard model, so you can predict the magnetic moment.
Very good. Yeah.
So how do you?
So good. That's a very good question. So what I can do is I can add masses to the neutrinos by modifying the standard model, but I can do it in a way that the only observable consequence of the new physics is a non-zero neutrino mass, and all the other consequences are very tiny. So in that sense, if I have a Lagrangian where the neutrinos got a mass through some mechanism that doesn't leave any other imprint, then I can still calculate what the neutrino mass and lifetime would be. But you're right. In general, if I modify the standard model to give the neutrinos a mass, I do all kinds of other things that probably will lead to a bigger magnetic moment than what you get out of the weak interactions, and a different neutrino lifetime that you would get out of the standard model as well. So it's kind of it's a minimalistic approach where you say, I know I need some new physics. I take care of that new physics. I say that the only observable effect of that new physics is a non-zero neutrino mass. Then I operate the rest of my calculation within the standard model. You can kind of do an effective field theory approach to this.
We used to hear of these Russian beta decay experiments, and also the scattering experiment. I don't know the status of this, I've not followed this subject for a while. There used to be other precision experiments with ions, pi beta experiment, N experiment, all these things. In principle, they should be able to give us at least some bounds.
Yeah, that's a very good question. There are a lot of different ways in which we can look for either neutrino masses or other properties of neutrinos. And they involve the kinds of measurements that you're talking about, precision measurements of reactor spectra, precision measurements of meson decays like pion decay and so on. For the purposes of observing the effect of a non-zero neutrino mass specifically, they are not competitive at all. So the best known example is, so there's a very nice way to try to constrain the neutrino mass, which is easy to talk about, which is to study pion decay. So if you take pion decay at rest, you know the initial state is a pion at rest, you know the mass. A muon goes one way, a neutrino goes the other way. You can measure the muon energy very well, and you know the muon mass. So by doing conservation of energy, you can infer the neutrino mass that way. People did that a while ago, and the bound on the neutrino mass that you get is about an MeV, a mega electron volt. And again, this is a really hard measurement, and you're measuring the muon momentum ridiculously precisely. So it's not competitive at all. It is competitive in different ways. So for example, many of the models that give neutrinos a non-zero mass, they predict the existence of a heavy neutrino. So imagine now you go back to your pion decay, and imagine that the pion decays into a muon, and another neutrino that happens to be heavy. Now if I measure the muon energy, and I have another neutrino that weighs like 10 MeV, I could see that. And that puts a very stringent bound on what the new physics could be. And I had this table in the very beginning that was just a kind of a cartoon, which is coming. And it was this one. And it's kind of telling you the types of phenomena that you would care about if you were interested in the origin of neutrino masses. And if the new physics is light, then beta decay and meson decays have a lot of power to look for these new states. Because if they're very light, they will show up in these types of processes unambiguously. But they're usually relatively weakly coupled. So the bounds are not competitive yet, but we're getting better. So I don't know if that answers the question. But yeah.
Also, neutron lifetime.
Absolutely. Neutron lifetime is another one. So that falls into the beta decay category, right? Yeah.
That is apart from electron, muon, and other things. So then would you expect also fourth lepton?
That's an excellent question. And That would be the simplest thing to do. You could add an entire fourth family to the standard model, and there would be a fourth lepton and a fourth quark and so on and so forth. And it turns out that that idea is completely ruled out. We have done it. We know that if it's what's called a sequential fourth generation, we know that all the new masses have to be less than something, and we haven't seen them. So we can, if you're very perverse, you can probably still fit a fourth generation in some way, but the vanilla fourth generation is ruled out. What makes neutrino special is that I can invent, so the neutrino, because it's neutral, I can introduce a new fermion that doesn't couple to anybody. It has no gauge quantum numbers. And that state is often called a stereoneutrino. Sometimes it's called a right-handed neutrino, just to confuse everybody. But it's a new gauge singlet fermion state. And what's nice is that I can add one of these particles, and I don't need to add a new fermion. I don't need to add a new charged lepton or quarks to cancel anomalies or anything like that. So that fermion I can add just by itself, and it doesn't screw up anything. It doesn't change my phenomenology in any big way. And if you do add a fermion like that, the only thing it can do is that it's allowed to mix with the neutrinos. So it's very easy to add more neutrinos as long as they don't couple to the W and the Z. So we like to call them stereoneutrinos. And I'm happy to talk more about that, but that's basically, we can't do that in a way that this new neutrino couples to the Z boson, for example. That's completely ruled out. But we're allowed to add these gauge singlet fermions, and they are perfectly allowed. By the way, a lot of dark matter models are exactly that, except that we don't let them mix with the neutrinos. But it's the same idea. You're adding a new particle that doesn't have any charge, and if it happens to be spin a half, it's allowed to mix with the neutrinos, and then it would show up in these oscillation experiments as long as the new states are not very heavy. If they're very heavy, the phenomenology looks different. But the physics is, the idea theoretically is the same. There's one question here in the front.
There are bounds on the type of degrees of freedom of number of neutrinos essentially coming from cosmology.
Absolutely, yeah.
What is the current status of that?
So you're going to hear about that in the afternoon. But I can give you a quick answer. So there are different bounds that come from different epochs. And the bounds are translated into the number of neutrinos. To be fair, these are not bounds on neutrinos. They're bounds on the amount of radiation in the universe. And they translate into about 3, which is suspiciously close to the number that we have. And they're getting better. So I think we can measure that at the 10% level. And so that's a really amazing thing that we can do. But again, it's just consistent with the idea that there are neutrinos. But it's still, we're still working on that.
You probably already mentioned this, but I missed it. Is it possible to measure individual neutrino masses?
That's a hard question. We don't know how to do it yet. And it does come down to the fact that we've never seen a neutrino mass in any experiment. In principle, if you do a beta decay experiment and you really measure the endpoint ridiculously well, you can in principle see the different neutrino masses. From cosmology, which you're going to hear about in the afternoon, in principle, you can see the effect of the 3 different neutrinos in your large-scale structure of the universe, and that should tell you one mass from another. In practice, none of this is true. This is all an in-principle thing. And that's always the challenge, that the masses are so small that we normally see an effective mass that's always some linear combination of the masses or the sums of the masses or things like that. So we're very far away from being able to say, I can do an experiment where I can see mass number 1 separate from mass number 2, separate from mass number 3. For now, we're stuck with the oscillations.
Follow up on that. In principle, if we were to measure the relic neutrinos,
Exactly.
also very sensitive to tell.
In principle, yes. It's the same kind of challenge. Yeah. So in principle, there's a way of measuring the relic neutrinos that depends on their mass directly. So you could say, the mass 1 will give me a little peak over here, mass 2, another peak. Not totally true because they have a spectrum that's a thermal spectrum, but in principle, yeah. So, but we're definitely not there. That would be it's a very hard experiment that even the great idea that we had recently seems to not work. So we need to go back to the drawing board to make the great idea actually work in the real world. There's some issues with quantum mechanics. Yeah, with the tritium, yeah, the Ptolemy, yeah. So basically what you need to do is you have to absorb a cosmic neutrino, and the cosmic neutrino induces an electron being emitted, and by measuring the energy of that electron, you have some information about the neutrino coming in and so on. The challenge is these are beta decaying nuclei, so they are also emitting electrons by themselves. So you have to tell the beta decay electron from the neutrino upscattering neutrino. And the problem is people said, oh, we can do this with tritium, and that would be super exciting. We take the tritium, we place it inside of a lattice of carbon atoms with graphite. It's very fancy. So they figured out that the tritium atoms are actually have a 0-point energy, so they're moving around, and that's enough to screw it up. So they're thinking about other things they can do with a similar idea. Anyway, that's the... So quantum mechanics is bad for us, for this particular case, yeah. You mean, you're asking about the plane wave approximation with yeah. So my very brief description of neutrino oscillations assumed that the states are perfect plane waves, and I also assume that they're perfectly coherent. So you have to go and you have to check if both of these hypotheses are correct. Of course, the neutrinos are not perfect plane waves. They are constrained into a wave packet. And once you take that into account, you also have to ask if the different mass eigenstates can form a coherent state. And it turns out that for all experiments we've ever done where we have seen the oscillation, they are perfectly coherent. So the plane wave treatment works very well. The opposite question would be, when doesn't it work? And what happens is, every time we can design a system where we don't think it works, we wouldn't have seen the oscillation anyway, because of other things, like the neutrinos are coming from very far away, or my energy resolution is not good enough. So it's very difficult to design an experiment where you can see a deviation from the plane wave perfectly coherent approximation that's not just a perfectly incoherent approximation. So we can see those two extremes really well. We don't know how to see the transition. We have no idea how to do an experiment that knows how to do that. We can do bounds phenomenologically, and we have done that, but the bounds are not in the realistic domain. They say that the coherence lanes have to be within some range, which is very, very safe. So we don't learn anything. But we're trying. I mean, it's part of, we need more better neutrino oscillation data. You know, the effect of losing coherence would be that instead of having a nice oscillation, the oscillation would dampen a little bit. We've never been able to see that in a way that's not just driven by the experimental details, because the experiments do that all by themselves. You know, the energy resolution, the distance resolution, things like that. So it's a big challenge. We don't know how to do it. We can talk about it, but we don't know how to do it.